Hey, welcome back to chemistry. And so now what I want to do is talk a little bit more about the odd behavior of electrons in atoms. So this is more on the development of quantum theory that describes atomic structure, and in particular the motions of electrons in atoms. And so now what we're going to do is describe something called the Heisenberg uncertainty principle. So here we go. So now here's where things were getting a little bit weird. So you might recall in an earlier presentation I was kind of mentioning the fact that electrons can actually be in two different places at the same time in an atom. Now I know that's very hard to believe. This is actually predicted by the pretty advanced mathematics that you use in quantum mechanics to describe electron behavior, but that is really the major implication, is that electrons can be found in more than one place at the same time. And so yes, this would apply for a single electron. One thing we're going to learn about now is that the mathematics of quantum mechanics predicts that even though you can find the electron in multiple places in the atom at the same time, there's really kind of a limited range. And so this range is defined by something called Heisenberg's uncertainty principle. Now here's sort of weird fact number two. So not only can you have electron occupy multiple places at the same time, it can have different speeds or velocities at the same time. So in other words, you can have the same electron going at 5 times 10 to the 6 meters per second, but it also may be going at 6 times 10 to the 6 meters per second. And so it can occupy these two different speeds or states at the same time, which sounds, I know, pretty unbelievable. But what the Heisenberg uncertainty principle will show you is that even though the electron can occupy different speeds at the same time, there's really sort of a range of speeds that can be predicted to be occupied by the electron when it's in the atom. So this is pretty hard to accept. And so there was a scientist that came along later in the 1930s named Schrödinger. And he had a lot of trouble accepting this idea as well. So he had this kind of fun analogy, which I'm going to describe to you, which it helps us understand that we cannot totally deeply understand electron behavior at the atomic level, is because it's stuff that we have never seen before in our macroscopic existence. So let me tell you what this analogy is about. It's called Schrödinger's cat. And so what Schrödinger suggested is, let's say you have just a regular sized cat. So there he is. And so let's say you put this cat into a box. And so there's the cat happily meowing away, unaware of the treachery that is about to befall it, because you are the dastardly scientist. And what you're going to do is you're going to put some radioactivity in the box along with the cat. And you know for a fact that there's a 50% chance that the cat will die within an hour once it's in that box. Okay, so you wait an hour, and so you know that when you open the box, you will pull out either a live cat or a dead cat. And there's a 50% chance of doing each. But importantly, you also know, just from common everyday experience, is that before you open up the box, if you pull out a dead cat, before you open up the box, the cat was dead inside the box before you pulled it out. Same thing with the live cat. If you pull out a live cat, that the cat was most certainly alive in the box before you pulled it out. But here's the thing. This is not how electrons behave. Now let's pretend that now our cat is the size of an electron. What would the cat be like in the box before you pulled it out? Well, it wouldn't either be alive or dead. Instead, it would be alive and dead at the same time. It would occupy these two same states at exactly the same time. It would be sort of a mixture of liveness and deadness. Now, I know that sounds very difficult to believe, but this is the prediction for quantum mechanics for very small objects, in that they can occupy multiple places or multiple speeds at the same time. However, if you were to pull this cat, the size of electron, out of the box, even though it's kind of in this mixture of live and dead within the box, but as soon as you pull it out of the box, it becomes either live or dead. So the actual act of measurement of a cat the size of an electron forces it into a final state of either being alive or dead. But importantly, what this principle says is that applied to electron, it can be at multiple states at the same time. It can have multiple speeds at the same time or multiple velocities at the same time. So this brings us to the Heisenberg uncertainty principle. And so now you understand electrons can be in a range of places at the same time, and they can also have a range of velocities at the same time. So what the Heisenberg uncertainty principle says is that the range of velocities, which is symbolized by delta V, that electrons can occupy is inversely related to the range of positions, which is delta X it can occupy in an atom. So we have an equation there, which is the Heisenberg uncertainty principle. And what you can see is that delta X, the range of positions, multiplied by the mass of whatever you're considering, usually an electron, times the range of velocities must be greater than or equal to that constant there. That's h, which is Planck's constant, divided by 4 times pi. So let's look at this equation a little bit more carefully. So you can see that delta x times mass times delta v must be equal to or greater than a constant, which is some arbitrary number. Now, what I'm hoping you can see is that if you look on the left side of the equation, imagine that you were to, for some reason, increase the value of delta x, meaning you were to increase the ranges in which you could find electrons in atoms. If you were to do that, in order that number to remain a constant, you would have to correspondingly decrease the range of velocities. So as the range of possible positions an electron or other small object can occupy increases, the range of velocities that electron must occupy decreases. So they're inversely related to one another. And again, the reason why that happens is just to make sure that the total range of velocities times the range of positions times mass is going to be above a certain constant. Another way you can restate this equation, and which is often spoken of this way, is one of the things you'll learn in physics is if you take mass of an object times its velocity, it's called momentum. So another way you can restate the equation is just substituting momentum, which is symbolized by P, for m times v. But if it's m times delta v, it would be delta p now. So we're now a change of momentum. So another way of saying Heisenberg uncertainty principle is that the range of positions, x, times the range of momentums, p, has to be equal to or above that constant. What the law basically says is this, is if you have a very narrow range of positions that the electron will occupy in an atom at the same time, there must be a correspondingly very broad range of velocities that the electron will have in that atom at the same time. In other words, if delta x is relatively small, delta v is relatively large. But it can go the opposite direction. If there's a very broad range of positions that the single electron will have at the same time, there will be a relatively narrow range of velocities it will have. In other words, if delta x now is very large, delta v will be really small. So now what we can see is, based on some of the things we've talked about with quantum mechanics, that we need a new model of an atom. So the model that we kind of talked about previously, which is the Bohr model, where electrons travel in defined trajectories in orbits around the nucleus of the atom. Although that model is pretty good about predicting for hydrogen where the wavelengths of the emission spectra will be, it really cannot be used for much of anything else. So for example, you can't even use Bohr model to predict the emission wavelengths for other atoms like lithium or sodium or anything like that. So the Bohr model is pretty limited in its use. So in 1928, in realization of laws of quantum mechanics that were being developed, a new model of the atom was created, the quantum mechanical model. It's also called the wave mechanical model of the atom. And so this was created by 3 men, Erwin Schrödinger in Germany, Werner Heisenberg in Germany, and Paul Dirac in England. All 3 got Nobel Prizes for their work. So this new model, the quantum mechanical model of the atom, was based on 3 ideas which I just kind of mentioned. That electrons, not only are there particles, but they also have a wave nature. And you might remember we used the de Broglie wave equation to understand to some degree where we can find electrons in the atom, how far away from the nucleus they are. Another thing that this new model of the atom uses is that Heisenberg uncertainty principle. Again, it's the idea that you really cannot determine accurately the velocity and the position of an electron at the same time. Another thing that is applied in this new model is one of Bohr's ideas was correct. Although you cannot describe electrons as going in orbits around the nucleus, Bohr suggested that in those positions at distances away from the nucleus, those electrons have certain energies, and that those energies are defined numbers. And so those energies are said to be quantized. And so putting this all together, what it basically says again is that when you have an atom, you're looking at electrons, we'll never know exactly where the electron is because we cannot define a trajectory for it. But we have some idea of the probability of how far away the electron will be from the nucleus. Now, there are equations that describe how far away from the nucleus these electrons will be found, and these are called wave equations or wave functions. And so the main equation that is used to describe where the electrons are truly found in the atom and generally how far away they are from the nucleus is called the Schrödinger equation. It's also called the wave equation. The reason why it's called the wave equation is due to Broglie's idea that when you have standing waves at a certain distance from the nucleus, only ones at a particular distance away will constructively interfere with one another, and you'll get a good standing wave that reinforces itself. And so it's at that relative position that you might be able to find an electron. Now, you can go a little bit maybe further out, and you can create other standing waves where you can find electrons. And so these standing waves are modeled using this wave equation, the Schrödinger wave equation. The only thing you really need to understand about that is that these standing waves basically tell you the regions in space where you're most likely to find an electron, where you have a high probability of finding an electron, and those regions in three-dimensional space are called orbitals. And one of the things we'll be talking about next is when you have this Schrödinger equation, which tells you all the orbitals that can exist around the atom, which define where the electrons are in the atom, these particular orbitals are defined by constants. These constants, there are three of them, they're called quantum numbers. And the quantum numbers are constants which are applied to the Schrödinger equation, which kind of map out the orbitals in space. So we will learn about these quantum numbers in the next lesson.